All right, let's dive in. Today, we're talking about how to tame the absolute beast that is serving large language models. It's a world where the line between the super snappy user experience and a slow, crazy expensive failure can come down to just a few key optimizations.
Okay, so here's the game plan. We're going to start with why this is so hard in the first place. Then we'll look at the software tools we have to fix it, get into the big debate on where to deploy these things, figure out what numbers we actually need to watch, and then we'll put the whole shebang together with a real-world example.
So first things first, why is serving these models so ridiculously difficult and expensive? I mean, it's the question that keeps a whole lot of engineers staring at the ceiling at 3 a.m.
Well, it really boils down to two kind of brutal realities about how these models work when they're actually running, what we call inference, and it's a whole different ballgame than training.
So, reality number one, the KV cache. This is basically the model's short-term memory of the conversation. And man, it just eats up your GPU's VRAM like a crypto miner in a bull run. The longer you talk, the bigger it gets. Then there's reality number two. Generating words is painfully slow and sequential. You literally can't create the next word until the last one is finished. This leaves your super expensive GPU just sitting there, twiddling its thumbs.
And this right here, this is the trade-off that's at the absolute heart of the problem. See, the KV cache is actually a super smart idea. It saves a ton of compute power. But the price you pay is this massive, massive memory footprint, which makes VRAM the #1 thing we run out of.
So it sounds kind of bleak, right? How do we even begin to fight back against these bottlenecks? Well, lucky for us, some really smart people have built an entire software toolkit to do just that.
And one of the first and biggest wins is something called continuous batching. I love this analogy. Think of it like running a restaurant. Traditional batching, that's like waiting for the entire restaurant to empty out before you let new people in. It's just wildly inefficient. Continuous batching is the smart way. As soon as one table frees up, you get a new group seated. It keeps the GPU working constantly and just skyrockets your throughput.
Some modern tools like vLLM, they package all these cool tricks together. We just talked about batching, but let's zoom in on quantization for a second, because this is another huge lever we can pull to save a ton of that precious memory.
Okay, so by basically using, let's call it lower quality numbers in that KV cache, we can get these insane memory savings. You go from the standard 16-bit format down to 8-bit, and bam, you just cut your memory usage in half. And with these new formats like NVFP4, which only use 4 bits, you can slash that memory footprint by 75%. That directly means you can handle way bigger batches or much, much longer conversations.
Now here's the magic part. We get all this efficiency without really giving anything up. You get these huge memory savings with like less than a 1% drop in the model's accuracy. For pretty much any application out there, that trade-off is a no-brainer.
So what happens when your model is just an absolute monster, too big for even one GPU? Well, that's when we turn to parallelism. Think of it like this. Tensor parallelism is like taking one giant, complex Lego piece and splitting it across a few builders. Pipeline parallelism is more like an assembly line, where each builder gets a whole section of the instructions. And in the real world, you pretty much always use them together to chop these giant models up across a whole fleet of GPUs.
Okay, so we know all the software tricks now, but where do we actually, run the model? And this brings us to what I like to call the great deployment debate. Do you build it yourself, or do you use the cloud?
On a high level, it's that classic business dilemma, CAPEX versus OPEX. Do you spend a ton of money right now to buy your own servers, or do you pay as you go with the cloud? On-prem gives you total control and privacy, for sure. But with the cloud, well, you're trusting someone else with your stuff.
So what's the tiebreaker? Well, a developer on Reddit just absolutely nailed it. The key, the whole thing, comes down to one word: utilization. Is your model going to be cranking out answers 24/7, or is your traffic going to be all over the place? And this gives us a super clear way to think about it. If you have constant, heavy traffic, paying for your own hardware by the hour is almost always going to be cheaper for each token you generate. But if your traffic is spiky or you just don't get that many requests, serverless APIs are a lifesaver because you're not paying for a really expensive GPU to just sit there doing nothing.
Okay, so you did it. You deployed your model. But how do you know if it's any good? You need the right metrics. I'm not talking about vanity numbers. I'm talking about metrics that tell you what's really going on.
This is the single most important question your dashboard should answer. Because at the end of the day, that's all that matters, right? The user experience. And the answer isn't just one number, it's a couple of very specific user-focused metrics. First up, time to first token, or TTFT. Think of it as the hello test. How long does a user wait before the model even starts talking back? For chat, you want that under 200 milliseconds. Then you track the delay between every other word. And this is so important. Don't just look at the average. You have to look at your P95, your 95th percentile. That tells you what your most important power users are experiencing, and averages can hide some really nasty problems.
Okay, so that's user experience. The other side of the coin is capacity. You have to know when you're getting close to your limit before everything falls over.
So for capacity, yeah, you look at your overall throughput, your tokens per second. But the real canary in the coal mine, your early warning signal, is the request queue length. If your traffic is flat, but that queue starts climbing, you've got a problem. You're saturated. And of course, you've got to watch that GPU memory like a hawk to see how close you are to tapping out.
All right, let's bring it all home. We're going to put every one of these concepts together with a massive, real-world example serving Meta's Llama 3 145 billion parameter model. Yeah. This isn't theory. This is how it's really done. And this is where you see how it all just connects. You start with a big cluster of GPUs. I mean, you have to for a model this size. Then you use both tensor and pipeline parallelism to slice and dice that model so it fits. Next, you deploy it with a smart inference engine like vLLM to handle all the tricky stuff like continuous batching. And finally, you are constantly monitoring those key metrics we just talked about, TTFT, TPS, and GPU memory, to make sure everything is running perfect.
So look how far we've come. We started with those kind of brutal realities of inference, that memory hogging, KV cache, and the slow one-word-at-a-time generation. And we ended up with a full-stack, practical solution, a toolkit that combines software, hardware strategy, and the right way to measure success.
You know, at the end of the day, there is no single best setup. It's always a series of trade-offs. You're balancing cost versus speed versus complexity. But now you have the toolkit to actually analyze those trade-offs. So the real question, the one I want to leave you with, is this. How are you going to use these principles for whatever you're building next?